Okay, so here are the means for our four groups, and here are the standard, the sum of squares values. And we're not going to do computations yet because we still have to do, what I want to do is to do the conceptual bases of this statistical test that we're going to do. And the statistical test is called the analysis of variance. Okay, so that's what it's going to be called, the analysis of variance. And I must admit, I wasn't the smartest kid in the class when I was in college myself, and the teacher was talking about analysis of variance, and all of a sudden the teacher started talking about something called ANOVA. Okay, and I'm like, wow, I thought we were just talking about the analysis of variance. Well, listen, folks, here it is. Analysis of variance. Analysis of variance. Okay, so that's where ANOVA comes from. All right, now I want to explain what this means and what we're going to do with the conceptual basis of analysis of variance, which I am likely to ask you about in an exam, the conceptual. We'll get into the computational afterwards, but here's the conceptual basis of this statistic. Okay, here's what we're going to do. We're going to calculate an F value. That's the letter that we're going to have for analysis of variance, right? We have z-scores, we have t-values, we talked about p, for probabilities and stuff, but this is going to be an F value. And sometimes people call this an F test. I would rather have you call analysis of variance. And here's what we're going to do. Here's the conceptual basis for this. We're going to look at the variability between, so let's do this, variability between groups, and we're going to put that over a measure of variability within groups. Okay, and I'll show you how to do this. But variability between the groups versus variability within groups this way. Really what we have here is a matrix of numbers. That is a 5 by 4 matrix of numbers. So we're going to get a value, a numerical value for this, and we're going to get a numerical value for this in the denominator. But I want to talk about where those values will be coming from. Okay? So let's do this. I'm going to put in, this is subject number 1, subject number 2, subject number 3, subject number 4, subject number 5, okay? And so on and so forth. Different people in each of these groups. Different people in each of these groups. And how many do we have all together? 20, right? We have 20 people all together. So here's what we have. 20 people, right? And here's what I'm going to do. For the variability between the groups, I'm going to look at, these are the components that go into this. We're going to get an overall value for variability between groups and an overall value for variability within groups. But here's what this means. Let's look at subject number 2, for example, and compare that to subject number 10. These are people in our experiment, right? And we're looking at between groups, between these two groups. I could also look at, this number, this person compared to this person, right? So we're looking at this, we're looking at this, I'm looking at this person compared to this person, right? All these between groups comparisons. And what I want to ask you, I'm going to make this a little bit shorter, so we're going to look at between groups, okay? I'm going to look at within groups, the variability. And here's what I want to ask you. Why might subject 2 and subject 10, right, they have different memories for different numbers of words. That's the data that we're looking at here. Subject 2 remembered 8. Subject 10 remembered 4 words, okay? Subject 7 remembered 5. Subject 19 remembered 7. And all these different between groups, okay, comparisons. Why might this person remember a different number of words than this person? Well, it could be due to the fact that they're in a different treatment condition. This person's in the quiet group, this person's in the Taylor Swift group. Or this person is in the quiet group and this person's in the white noise. This person's in the Taylor Swift, this person's in Taylor Swift without lyrics. So the reason that we may see some of those differences is because of the treatment, okay? Which is really what we want to address when we're doing our research. I want to know if the treatment's causing a different effect, okay? But why else might these two remember a different number of words? Or why might this person remember a different number of words than this person? Well, I'm going to do this. It could be due to, and I'm going to make this a bag, okay? I'm going to make this a bag with a bow on it. And I'm going to call that individual differences. And I'm going to make that a plural, okay? This person's female, this person's male, this person's 20 years old, this person's 18 years old, this person had their breakfast this morning, this person didn't have their breakfast this morning, this person has brown eyes, this person has blue eyes, this person has a higher IQ, this person has a lower IQ. I mean, individual differences could be a whole bag of things. So that maybe this person remembered more words than this person, not because of the music, but because of the fact that they had orange juice and a bagel this morning for breakfast, okay? Maybe this person remembers more than this person because they got a better night's sleep than this person. Maybe this person remembers fewer than this person because they just don't give a damn to do well, okay? What I'm saying here is any differences that we see between groups could be due to the treatment, but could also be due to individual differences or some kind of combination, okay? I'm not making a judgment here about what I think is happening. Individual differences could be explaining this, or treatment could be explaining it, or some combination. There is a third component to this potential explanation for between groups differences, and that is whenever we make a measurement of any sort, whether I'm measuring your height, whether I'm measuring your weight, whether I'm measuring your running speed, or whether I'm measuring the words that you can recall, I could have a measurement error, okay? Now, if you are aware of this error, then you do something about it. But what I'm saying here is maybe this was a 9, but when my research assistant wrote it down, it looked like a 4 to me, okay? Or maybe the person wrote half the words on the front and half the words on the back, and I just counted the words on the front. I mean, that would be sloppy of me, but it's a possibility. So we're going to call this measurement error, and that's a possibility for any differences we see. Let's hope that that's a small component of potential differences that we see, okay? But it's there. Well, our goal here, our goal when we do this statistic is to try to see if there's a difference between the groups. Unfortunately, whatever between group variability, because variability is difference as well, it's just lots of differences, right? We can't tell if it's the treatment or individual differences or measurement error or some combination of the three. So therein lies the problem. But let's see if we can't figure this out. We're going to analyze the variance, analysis of the variance in these numbers. Okay? So let's see if we can figure this out. Let's look at within groups. So I'm going to use a different color here, or maybe a different shape. I want to look at the variability, the variance that we see within a specific treatment group, right? And so here's this person, subject 11, and here's subject 13. They are within the same group, right? Within groups. I'm going to say, gee, why are those people, why do they have different memory for different numbers of words? Well, I know that the difference here is not due to the treatment, right? Because they're in the same treatment group, just like this person and this person, right? Same treatment group. And so if they're in the same treatment group, the within groups variability cannot be due to treatment. So it's not treatment. This person is a different person than this person. This person may have slept 8 hours last night. This person may have slept 4 hours last night. This person is 6 feet tall. This person is 5'2". This person's male. This person's female. This person has 4 siblings. This person has no siblings. I mean, I'm just trying to make the point here that there's lots of individual differences, and certainly that could contribute. So I'm going to put this bag of individual differences down here. Okay. Oh, that's a terrible bag. I'm going to call this individual differences. Okay. Just like the numerator. Like I said, whenever we make any kind of measurement, there's always a possibility for error. So any of the within group differences should or could be a result of measurement error. Again, if you know that there's measurement error, then it's up to you to fix it. But even when you've done your best job at fixing these things, there's possibility for error. Well, it seems like we still haven't solved our problem, right? What do I want to know? I want to know whether there's a difference between these 4 groups. Treatment, individual difference, measurement error could contribute to any differences this way. Any differences this way, of course, don't involve treatment at all. It involves individual differences plus measurement error. This is what I want to get at right there. That's what I want to get at, but it seems like there's lots of other stuff going on. So, here's the solution. Very important. I'm going to make 2 more assumptions. Remember, we've made the assumption of homogeneity of variance, that these variabilities should be equivalent. We would use Hartley's F max if we suspected that they weren't. We're just going to assume equivalence for right now. But I'm going to make 2 additional assumptions. I'm going to assume that the average contribution of individual differences that we see this way between groups, that the average contribution of individual differences to the between groups variability is going to be equal to the average effect of individual differences within groups. So the influence of between and within, I'm going to assume are equal. Now, that doesn't get rid of it, but it makes this equal to this. Okay, that's going to be my assumption. And I tried to make the bags somewhat similar. I am also going to assume that the influence of measurement error, which I hope is small, that measurement error could influence between subjects' variability in an equivalent way as it does within subjects' variability. So, within the groups. So I'm going to assume that measurement error here and here are equal. So these two things should be equal. These two things should be equal. These two things should be equal. These two things. That's my assumption. Now, I have a question for you, my stat students. If the null hypothesis is true in reality, which would mean what? Which would mean there's no treatment. If the null is true, that there's no treatment, and if we have the assumption that these two are equal and these two are equal, then what would F be equal to? If there's no treatment, if the null is true, what would F be equal to? Now, some of you might think 0, and I'm like, well, wait a minute. I mean, you're probably suspecting that it's something special, but listen, if there was no treatment, if we have equal on top as on the bottom, and we're going to actually get numbers equal here to this. If this is 563 and this is 563 and this is 4 and 4, then we have 567 over 567, right? So what would that ratio equal if the null is true? The answer is yeah, it would be equal to 1. It would be equal to 1.00, okay, if the null is true. So now we're going to back up that logic and we're going to say, so when we do the computations, we'll actually get a value for F, okay? When we do the computations, if it's more than 1, then we can start to suspect that there's a treatment, okay? If the value is 1, then we don't have treatment. If the value is more than 1, then we do, okay? Based on this conceptual. I want you to know this for sure, okay? The conceptual basis. We're looking at variability between, we're going to compare it to variability within. Okay? So, to do our analysis of variance, we are going to create, okay, you guys have this in your notes, right? We're going to create, can you fit it in here? We're going to create an analysis of variance, ANOVA, summary table. Okay? Oops. And here's what that's going to look like. I'm only sort of questioning here. I need a little bit more room. So I'm going to move this stuff over a little bit. Okay? 9, 8, 7, 8, 8. For the white noise. For the Taylor Swift, 10, 6, 7, 7, 8. Okay. That's the Taylor Swift without lyrics. Okay. That gives me more room for my analysis of variance summary table. So here's what we're going to do. We're going to talk about the source of the variability. And in fact, this is going to be between groups, within groups, and the total. Okay? 3 items. Between groups, within groups, and the total. We're going to have a column for SS. We're going to have a column for degrees of freedom. We're going to have a column for MS. Okay? Now, and we're going to fill all these. Here's what we're going to do. Sum of squares for a total. And make a note of this in your notebook. Okay? Sum of squares total. That means we're going to treat these 20 numbers as if they were just a group of 20 numbers. And what we're going to do is we're going to get the overall sum of squares for those 20 numbers. All right? Let's do that right now. Just treat them like 20 numbers all together. Can we do this? Because I know my squares for single numbers, so that's good. Let's see if we can do this without a mistake. 49 plus 64 plus 81 plus 81 plus 64 plus 16 plus 25 plus 36 plus 49 plus 16 plus 81 plus 8, plus 8 plus 56 plus 49 plus 64 plus 64 plus 100 plus 36 plus 49 plus 49 plus 64. So I think that this is our first. I'm just doing the sum of squares formula for the total. So I just squared each of these numbers and added those together. I'm going to do it again just to make sure we have the right number. 49 plus 64 plus 81 plus 81 plus 64 plus 16 plus 25 plus 36 plus 49 plus 16 plus 81 plus 64 plus 49 plus 64 plus 64 plus 100 plus 36 plus 49 plus 49 plus 64. Hey, I got the same number. Pretty good. Okay. I always double check my numbers. I mean, of course I'm going to double check my numbers. Now I need the total for all of the scores, and then we're going to square that. Okay. I need the total for all the scores, and I'm going to square it. Wow. Okay, I can do that. 7 plus 8 plus 18 plus 8 plus 9 plus 13 plus 4 plus 17 plus 15 plus 8 plus 16 plus 14 plus 8. I think it's 145 squared divided by 20, right? We have 20 numbers. Of course, I'm going to check this value again. I'm going to start with this side and add backwards, okay? So 16 plus 14 plus 8 plus 17 plus 15 plus 8 plus 9 plus 13 plus 4 plus 15 plus 18 plus 8. 145. Okay. Square that number. Divide by 20. 1051.25. Okay. So the sum of squares then for all 20 numbers, right? 1101 minus 1051.25. 49.75. That's the total, the sum of squares for these 20 numbers. That's our building block for the variability for these 20 numbers. What are the degrees of freedom for a group of 20 numbers? The degrees of freedom is 19, right? It's n minus 1. So if I'm talking about these as an entire set of 20 scores, then 20 minus 1 is 19. Okay. So far, so good. It's just a big old fat sum of squares. For the within groups sum of squares, so I'm going to skip the between groups for a minute. For the within groups sum of squares, the within groups sum of squares is, so if we do this, within groups, sum of squares within groups is equal to the addition of the sum of squares for each group. We've already done that work here, 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 and here. Okay? So I'm just going to add up those sum of squares for each of the groups. Let's just add up those sum of squares for each of the groups. 2.8 plus 6.8 plus 2 plus 9.2, 20.8. 20.8. Okay. Now, degrees of freedom. This one is a little bit more difficult. Take notes, that's all, right? For the within groups degrees of freedom, what we're going to do is we're going to take the degrees of freedom for each of these sum of squares. Whenever you do a sum of squares, however many numbers that you're looking at to get this sum of squares, degrees of freedom are this many minus 1. So in this case, 5 minus 1, so degrees of freedom here is 4, right? Degrees of freedom here is 4. Degrees of freedom is 4. Degrees of freedom is 4. Just like we added up the sum of squares for the within groups, we're just going to add up the degrees of freedom. 4 plus 4 plus 4 plus 4 is 16 degrees of freedom. Okay? We're almost there. The next computation is a little bit challenging. Let me get my eraser here. A little bit challenging, something new for us. I'm going to do this as well. Okay. And this is a formula you don't have to memorize because you'll have it. So this is sum of squares between groups. And here's what it equals. We're going to add up t squared over n minus g squared over big N. Okay? Now, just take it slowly, okay? Here's what this is. The T here stands for the total for each of the groups. It's like treatment total, right? The T. The N is the number of people in each of the groups. T is the total for each treatment, okay? N is the number of subjects for each treatment. We're going to add those together. So in this case, we're going to have 4 of these. I'll show you, okay? Minus, now what is G? G is the grand total. That is the total of all 20 scores. What did we say that was? 145, I think, right? And then N is the grand total of, it's all the people in the study. So let me expand this a little bit. I'm going to get rid of this sigma, but you should understand what that means afterwards. Here's the formula. But here's what we're going to do. We're going to do the total squared for treatment 1 over N for treatment 1. The total squared for treatment 2 over N for treatment 2. The total squared for treatment 3 over N for treatment 3, right? Now, which is easier, that one or the one with sigma? I mean, the one with sigma works because you can do it for 5 groups, for 3 groups, for 12 groups, whatever. Okay? But this is the expanded version so that you understand it. So what's the total here? Now, please, this is the most common mistake, and it will mess you up in terms of your analysis. This is not the total. This is the mean. Okay? The total for group 1, let's do the Q group, right? The total is 41. Okay? So it's 41 squared over 5. The total here is, what was it? 5.2 times 5, that's 26, right? Yeah, 26, okay? The total here is 40. The total here is 38, okay? So now we can do this formula. It is 41 squared over 5 plus 26 squared over 5 plus 40 squared over 5 plus 38 squared over 5. And by the way, I don't do this by hand when I'm doing my research in my lab because I'll use the computer. Why are we doing it by hand here? I want you to see where these numbers are coming from. Okay? So G is the grand total of everything, and it's going to be 145 squared over 20. Okay? So let's do this. Can we do this? 41 squared divided by 5. 336.2. (26 squared divided by 5). 135.2. 40 squared divided by 5. 320. 38 squared divided by 5. 288.8. Okay. 145 squared divided by 20. 1051.25. Okay, let's get this. 336.2 plus 135.2 plus 320 plus 288.8 equals minus 1051.25. 28.95. Okay. Now I want you, so computations, right? Well, it's nice when you can understand the formula, right? The sum of each treatment squared over the n. When you say sum, then you're saying there's a number of these. In this case, there's 4 of them, okay? And then g squared over n, okay? The total number of people, the grand total squared. That's the formula. Here's what I really want you to notice. Guess what? The total variability is how much variability there is in these 20 numbers. Here it is, 49.75 for the sum of squares. But do you notice the relationship here? The total is made up of the variability between groups plus the variability within groups. So this is a matrix. Between groups this way, within groups this way. and they both add up to the total. And there's nothing left over, and there's nothing shared between these. And in fact, we call this relationship between these two orthogonal. What does orthogonal mean? Orthogonal means that the between groups and the within groups are separate sources of variability. There's no overlap. And they both make up the total. So we have between groups variability going this way, between groups going this way, within groups going this way. Okay? One more number that we need here. What about the between groups degrees of freedom? This one is a little bit trickier, and the book will say it's K minus 1. You're like, all right, what does K mean? K is the number of treatments. So how many treatments do we have in this experiment? 1, 2, 3, 4 treatments. So it's 4 minus 1. Between groups, it's the number of treatment conditions minus 1. For within groups, we're getting the degrees of freedom for each of these and then adding them together. So we have 3 degrees of freedom. And you will also notice the sum of squares add up, degrees of freedom add up. Okay? The total is made up of between and within. The total is made up of between and within. Now, what is MS? Well, this is the sum of squares. This is called the mean square. And what we're going to do is MS is equal to sum of squares divided by the degrees of freedom. Okay? So for the within, we have 20.80. 20.8 divided by 16 equals 1.30. Okay? What about for the between? Well, it's 28.95 divided by 3. So 9.65. Okay? And we'll do the total, even though we don't need it. 49.75 divided by 19 equals 2.62. Notice this is where the relationship falls apart. That is, these two do not add up to this. The degrees of freedom add up, and the sum of squares add up. Sum of squares add up, degrees of freedom add up, but it doesn't work for mean square, because that's like an average, okay? Oh my goodness. Doesn't this give you a headache, right? We still need to calculate our F value. Remember, the F value is the between groups over to within groups, right? That's the conceptual, but here's what we're going to do. We're going to get MS between over MS within. So let's do that. 9.65 divided by 1.30. So 7.42, okay? 7.42 is our F value. Now, do you remember? The logic, the conceptual basis of the F ratio? We said, well, if there was no treatment, we expect this value to be about 1. Because individual differences and measurement error, individual differences plus measurement error, right? Look back at your notes. We have a value that's greater than 1. But of course, this is not arithmetic anymore, right? What do you think we're going to do with that value for F? We're going to look up a critical F value. We're going to look up a critical F value, and compare what we observe to my critical. Because you are correct when you remember that if this is greater than 1, there's some evidence for a treatment. But like all the things that we've done, we got to say, well, is it really bigger than 1? I mean, is 7.42 big enough larger than 1 for us to, reject the null? So we're going to pick that up in the next video, okay? We will look for a critical value, and for the next video, you're going to want to have your book handy, because I'm not going to make a handy dandy, excerpt from that, but you'll need to look at the analysis of variance table. We'll need to look at the critical F value for this arrangement of numbers, okay? So we will pick up on that. Make sure you have your book handy, because we're going to look at this kind of complicated table, but I'll help you through it.